thesis is entitled The Mixed Integer Linear Programming Approach for Designing Cortical Visual Prostheses. I would like to dedicate this thesis to my parents and all those who raised me and supported me throughout my life. Every research should have a philosophy. Our research philosophy is that the insight gained from solving problems is more important than solving the problems themselves. Based on this, we can say that there are two lines of thoughts behind adopting solution strategies. The first school of thought prefers seeking general, complicated solution methods that can solve any problem, no matter how complex this problem is. They seek general problem-solving approaches. The second school of thought prefers to study each problem, tends to be more problem-specific instead of being general. Every problem is studied, and based on this study, the problem can be mapped to a problem that is solved, that is readily and already solvable using rigorous methods. A rigorous method is a method that conclusively decides whether a defined problem is feasible, and when finding a solution to it, it can say whether the found solution is optimal, and if it is not optimal, it can say how far it is from that optimal. We adopt this second line of thought, this second school of thought, as we believe it helps in gaining insight and in promoting knowledge. To demonstrate our point of view, we decided to adopt the problem of cortical visual prosthesis design because it is a challenging problem. Of course, visual impairment is very important, is a very important research field. Handling it, dealing with it, and solving, and trying to help visually impaired people is very important, because visual impairment greatly affects the life of the patients. There are many causes of visual impairment that are not repairable. It's no remedy for them exists. It has been well known since long ago that problems with lenses, with eye lenses, are solvable using eyeglasses. The approach behind eyeglasses, they deal with the visual impairment rather than solving it. So, following this, researchers decided to seek a solution that deals with blindness instead of solving it. The solution is the visual prostheses. Visual prostheses depend on the rationale that if presenting an image to a healthy person results in a pattern of electrical activity along the visual pathway, that the opposite would be possible. If we impose the electrical activity, the expected electrical activity pattern on the visual pathway corresponding to a certain image, that the blind person will feel or perceive the image even if it is not present, even if he cannot see it actually with his eyes. The challenges of visual prostheses. Why is it a challenging problem? Mainly because the visual pathway is very complicated. It consists of different visual areas. Each visual area consists of different layers. There are connections between the different areas and connection between the different layers. There are feedback connections and feed-forward connections. There are different types of cells. And so, of course, the whole visual cortex is very small, so we have in a very small packed area, we have different cells, very different connections. It's very difficult to impose the exact required pattern of activity on them. In addition to that, we find phenomena like eye saccades. Saccades are eye movements, a type of eye movements. Its speed about 900 900 degree, it's 900 degree per second. Okay, 900 degree per second. That means that the 900 different images per second enter the brain and are processed. Of course, all this means that the brain expects corresponding to a certain image a very complicated pattern of activity due to the different cell types and different connections, and due to saccades. It's very difficult to impose this pattern, and if the pattern imposed is inconsistent, we find that perception fails. Okay, and this is why the progress in visual prosthesis has been very slow, and what we succeeded in doing actually is just making the patients perceive light spots that we will call that are called in literature phosphenes. We adopted based on an engineering thinking. We try to adopt a simple problem. Perhaps it does not satisfy the ambitions of the application of designing a prosthesis, but we know that from solving it we can learn, and without solving it we can't really design the full desired visual prosthesis. So we start by a simple example. If we can design this example accurately and analyze the results, then we can promote after that our ambitions to more challenging design. In our design, we want to show the blind person a sketch of the environment that is plotted using phosphenes. So the blind person will not actually see the environment or perceive it. Instead, the blind person will perceive a sketch of the environment that will appear in a part of his visual field using these phosphenes. And the sketch of the environment is application specific. Our application will be obstacle avoidance. And so what we aim is to show the blind person in a part of his or her visual field a set of phosphenes sketching the locations of obstacles in the environment. Okay. The application should proceed as follows. There will be a camera or any other sensor from which we can decide the location of obstacles. After the location of obstacles are decided, we use a retinotopic template to find the correspondence between the locations in the visual field and the locations that should be excited in the brain. Once again, it's not necessary to show the locations. They should not occupy. It is not necessary that they occupy the whole visual field. It's a sketch that will be shown in a part of the visual field, and the blind person will get used to this by training. He'll know that this part of the visual field is actually showing the whole environment, the obstacle distribution in the whole environment. Okay. For practical implementation, electrode arrays can be used. The electrode arrays are actually placed on the surface of the cortex, but they include penetrating pins. The length and location of pins define where the injected currents which parts of the brain will be affected by the injected currents. Okay. So depending on the length of location of the pin, this will define where exactly within the cortex the current will be injected. Okay. Based on this, it is our design goal to find the best locations of to inject where to best inject the currents, and what values of currents should be best used, so that we can actually stimulate locations that accurately reflect the locations of obstacles in the environment. So, okay, so we want to have very good control on where the phosphenes will appear, because where the phosphenes will appear in the visual field will actually convey to the patient where the obstacles are in the environment. Okay. Based on our research philosophy, we want to determine where to place the electrodes, where to inject the currents, and where and what values of currents to use. Okay, based on a rigorous approach. We want to use a rigorous approach that for this purpose, of course, we need to simplify to be able to map the problem to a problem that is already solved in literature using a rigorous method. We need to adopt some simplifying assumptions. Okay, after adopting these simplifying assumptions, we will find a mapping to a suitable problem that has a rigorous solution. Okay, when attacking any problem, we will discuss what is our objective from our computations and what performance measures are used to assess to what degree we did satisfy this required objective. In addition, of course, to the control variables that are available to us that we can manipulate to achieve the desired objective. Now we will discuss our assumptions. Adopted assumptions that we use to simplify the problem is first we assume the differences between a healthy person and a blind person retinotopic from a retinotopic point of view is limited, and so we will use the retinotopic template of Benson that is actually obtained from data of healthy subjects. We will use it in our calculations. This implies that we are working on cases that are not really late blind cases. The second assumption we assume is that we will not use any signals faster than 90s of megahertz. Based on this, then we can Poisson equation can be used to predict the field distribution with reasonable accuracy. Okay. We will use effective conductivities. The fact that the conductivities are anisotropic will not be considered. Both electrodes and neurons are assumed to be point. We use point electrodes and point neurons. Okay. We assume that the state of the brain is mainly influenced by the stimulation currents, the stimulation field. Okay, that means the secondary input due to the connections between the neurons themselves are not considered. Of course, each neuron receives input from the field, from the stimulating field, and from the other neurons it's connected to. We assume that the stimulating field is stronger and that it dominates. Okay, any other inputs are considered as noise. Neurons, as we said, are considered point pyramidal neurons. Based on this, we assume that their direction is normal to the cortex and that we can predict the response by solving a single compartment Hodgkin-Huxley model. Okay. We also assume that a phosphene is evoked as soon as the location, the brain location corresponding to this phosphene is stimulated with a field that is just higher than the minimal firing rate of this location. Okay. Of course, these assumptions are simplified. Of course, the real picture is more complicated, but our point of view is that although these are simplifying assumptions, okay, researchers using these assumptions proved that the models based on them have good predicting power, good prediction power, meaning that when they use these assumptions to build a mathematical model, okay, the predictions from the mathematical model are close to the data obtained from practical measurements. This means this justifies the using these assumptions. Okay. The first problem that we will discuss is the reachability problem. Reachability problem means that we want to find our goal in it is to find the minimal number of electrodes that can excite the locations that we want to control in the brain. Okay, in this problem is not a main problem that we're concerned with, but it just helps us so that we don't start in other problems that matter to us with a very small number of electrodes that's not adequate. So first we start by solving the reachability problem, meaning that we want to find the minimal number of electrodes that can derive with which we can excite all the locations we want to control. Okay, so our goal is to find in this problem is to find the maximum current. We start with a small number of electrodes, and we find the maximum current that can be, of course, under a safety constraint, that can be delivered to each of the locations considered. Okay, if the maximum current deliverable to each location considered is greater than its excitation threshold, then this neuron or this location is excitable. Okay, so if the maximum is less than the threshold, we call this neuron or this location unreachable. We cannot excite it. The main variables we use here are the electrode currents. Are the electrode currents. Okay. The second problem we discussed is the focality maximization problem. By focality, a setup, an electrode setup is called focal. Okay, a stimulation setup is called focal if it can excite any desired location alone, selectively, without exciting its neighboring locations. We want to emphasize something. When we mention, I use usually the word neuron and location exchangeably. We understand that of course, there is a resolution in our study based on finite resolution, based on that is much less actually than the number of neurons in the brain. So when we talk about location, we mean that we assume that if any of the neurons in this location reach the excitation threshold, then phosphine would be evoked. Okay, so the stimulation is focal. If when we target a certain location, we can excite this location selectively alone without exciting its neighbor location. Okay, so our objective is to maximize this selectivity. Okay, meaning to minimize the number of locations that are excited by mistake. When we target a certain location, only it should be excited. Possible control variables are two sets of variables: the electrode locations and their currents. Okay. For performance measurement, there are different measures. First, there may be a measure, as we said, the selectivity. Selectivity can be judged based on two measures. A direct measure is based on the number of locations that are excited by mistake, NUD. Okay, so as the number of locations excited by mistake increase, the focality decreases. This is one measure. Okay, the second measure is based on the visual error. Since our application is a visual application, okay, so if the phosphines excited by mistake or evoked by mistake due to excitation of locations that should not have been excited, if these phosphines that are evoked by mistake are close to the phosphine that we really intended to evoke, then the error should be considered small. That's why we define a term that is the visual error, and the visual error is based on the distance between the phosphine evoked by mistake and the correct phosphine that should have been evoked. Okay, and we sum these visual errors. Our objective is to minimize this sum, so that when we tend to excite a certain location, even if locations are excited by mistake, we tend to favor that they are close to, that they result in evoking phosphines that are close to the phosphine that should have been evoked. Okay, so these are two measures. There is also a probabilistic measure that takes into account the uncertainty. Of course, we made modeling assumptions, and these modeling assumptions means that our calculations are not perfect, are not perfectly accurate. So we need to include some safety factor. Our safety factor is, in our design, we tend to use two thresholds. We consider a location to be excited with 100% certainty if it exceeds a certain excitation threshold, and we consider a location to be unexcited, not excited, with 100% certainty if the current delivered to it is lower than a certain threshold. So we use two thresholds. In between these thresholds, the response, due to the modeling uncertainty, the response between the response of the locations or neurons is probabilistic. Okay, depending on the value of the delivered current relative to both thresholds. So we can also use a probabilistic measure. Okay, we can weight the visual error with this probabilistic measure to get a visual error that is closest to reality, instead of using a best case or worst case approaches. The second problem we address, the third problem we address, is the complex pattern fitting problem. In this problem, our objective is to impose a complex activation pattern. We will, among the locations we are studying, we will design which locations are desired to be excited and which locations are desired to be unexcited. The faculty problem, we studied in each problem is actually a set of problems. In each problem, only one location is desired to be excited. This was the focality study. Here, this is actually the problem corresponding to that actually needs to be solved online by the prosthesis, corresponding to a certain set of objects of obstacles. We decide that a certain set of phosphines should be evoked. Okay, and we want to evoke them, and to evoke these phosphines, we decide which set of brain locations should be excited and which should remain unexcited. Okay, so our objective, once again, is as much as possible to excite all the locations we want to excite with minimal additional excitations. Once again, there are several measures to assess the performance of a certain solution. The first measure is inconsistency. We compare the number of locations that have been excited with those that we intended to excite, and we compare the number of locations that should have remained unexcited with those that actually remained unexcited. So we study the inconsistency, to which degree we did achieve our goals. Okay. The second performance measure is probabilistic. We take into account, if we use just the first measure as it is, that this means that we either use a best case design or worst case design to decide which locations are excited and which are not excited. If we want to use a probabilistic approach, we take into account the two thresholds issue, and based on this we calculate an average probability of failure. Of course, the probability of failure, meaning failure for a location that should have been excited, is not exciting it, and failure for a location that should have remained unexcited is exciting it by mistake. So we compare the value of the delivered current at these locations with the intended or desired thresholds. The further it is from the target's threshold, the more we are closer to failure. This is the probabilistic approach. Okay. Alternatively, we can use the visual error. It's not important which locations are excited and which are not excited. What we really intend is we see those locations that have been excited by mistake, how far are they from the intended phosphine locations? If they are close to them, the visual error is small. So this is the approach we take. Of course, the visual error again can be compared based on a worst case or best case, based on worst case or best case thinking, or it can be computed based on a probabilistic thinking by comparing delivered currents to the intended thresholds to achieve the goals of each location. A common problem between all problems we studied up till now is the problem of estimating the value of electrode currents. How to estimate the value of electrode currents, okay? Whether to achieve a focal setup or to achieve a certain desired complex activation pattern. There are different approaches to this problem. The first approach is the conventional approach. The conventional approach is a guided trial and error approach. If we have a set of electrodes, we inject a current in each electrode. We increase this current gradually until the electrode results in the evocation of a certain phosphine. Okay. Once this happens, we record down that this electrode can evoke a phosphine at a certain location, and this is done for all electrodes. When we want to impose a complex pattern, or when we want several phosphines to be evoked at the same time, we inject the recorded currents in the related electrodes. Okay, this is the conventional approach, and it's the main approach used in most applied practical prostheses. Okay, the second approach is a nonlinear approach. Nonlinear approach looks to the problem as a black box. We have a simulator. This simulator takes it doesn't dwell into the mathematical details. It looks at the problem as we have a black box simulator. The black box simulators, the input to it are the electrode currents, and the output whether which locations are excited and which are not. So this is the input and this is the output. Based on this point of view, we have a nonlinear problem. The relation between the injected currents and whether locations are excited or not is a nonlinear relation. And if it is a nonlinear relation, then we have no choice but to use a heuristic method to solve this optimization problem. The main heuristic method adopted in our work is the particle swarm optimization method. The other approach, the other thinking or an alternative approach is the using quadratic programming. When we use quadratic programming, now starting from here, we start looking at the mathematical details of the problem. Since we are using a quasi-static approach and using Poisson equation for modeling, then we assume that the relation between the delivered currents, okay, at the brain locations, and the injected electrode currents, this relation is linear. Okay, so we will look at our mathematical model that it is composed of two parts. The first part is a linear part, where the delivered current at brain locations are related to the electrode currents using the linear Poisson equation. Since they are related using the linear Poisson equation, the relation between both currents can be computed by using a transfer matrix that is readily computable based on simulation results. So we have a transfer matrix that can be multiplied by electrode currents to give the delivered currents. Okay, if we have these linear relations, then we can formulate our problem as a quadratic programming problem. Why? Because although whether a location is excited or not is based on the nonlinear Hodgkin-Huxley model, okay, we can solve this linear Hodgkin-Huxley model offline to determine certain desired values of delivered current. Based on the solution of Hodgkin-Huxley model, we can decide thresholds. We can decide what values of delivered current are desired at the different locations so that they remain unexcited or to excite them. Okay, once uh, the desired delivered currents are computed, then our problem is a linear problem. We relate that relates that is related to the relation between the desired delivered currents and the control variables, which are the electrode currents. Okay, this is a quadratic formulation, of course subject to safety constraints. The disadvantages of this approach are as follows. For the conventional approach, it assumes some certain the superposition applies. If we know the currents the current that if injected through each electrode excite a certain phosphene, if we want all phosphines to be excited together, we excite the electrodes together with the currents recorded. This is not accurate actually, because even the location when we inject a certain current in an electrode, it results in a phosphine at a certain location, but this does not mean that the other neurons corresponding to other phosphines are not affected at all. They are affected slightly, but not to the degree of being excited. So when we excite the electrodes together with the recorded currents, not only the intended phosphines are excited, many other phosphines are excited by mistake. So this superposition assumption embedded within the conventional approach is not actually accurate. Okay, the nonlinear approach. The nonlinear approach is over complex. It does not study the problem in detail. Many simplifying assumptions can be used. The problem is not really nonlinear, because we have, although the reaction of the neuron is nonlinear, okay, it is predictable using based on the desired delivered currents. We have a certain desired values of delivered currents that, if they are imposed on the neuron, they result in a certain predicted desired performance. So actually, instead of relating the response of neurons to electrode currents directly, we can relate them to the delivered currents, and delivered currents can be predictable by solving the nonlinear neuron models offline or any other suitable method. So the problem is not nonlinear. So by using nonlinear method, we are we are liable to be trapped in local minima. The satisfying constraints become complex, and these complexities are all not necessary. They can be avoided. For the quadratic formulation, its problem is it's not accurate. A quadratic formulation, the quadratic objective function computes the Euclidean distance between the desired delivered current density and the actual delivered current density. Okay, the Euclidean in computing the Euclidean distance, we imply that whether the delivered currents are slightly higher than those required or slightly lower, that both are equally good. This is not actually accurate. If we want, it is based on our target, our goal. If our goal is to excite a location, if the delivered current is higher than the desired threshold, this is a good thing, and if it's lower, this is a bad thing. The opposite is true for locations that are required to be not excited. Okay, so the quad formulation does not really accurately represent our objectives. This is its problem. Now, our proposed approach. Our proposed approach is close to the quadratic formulation. It uses the same principles. However, it is a perfectly linear approach. It's a linear approach. Instead of we looked at the problem from a different point of view. We looked that it's a multi-objective problem. Our multi-objectives are that we require certain locations to be excited. So we have an objective associated with each location, which is whether we desire it to be excited or whether we desire it to remain unexcited. Okay, whether a location is excited or not is actually a constraint. It's a constraint. If the delivered current at it is greater than the excitation threshold, it will be excited. If it is smaller than the excitation threshold, then then it will be unexcited. Of course, as we said, for safety, we use two different thresholds for excitation and unexcitation. Okay, so we actually look to the problem is that we have a set of constraints, a constraint defined for each location. We want these constraints to be satisfied as much as possible. This is called a minimum. That is, we look for the minimal breakable set of constraints. Okay, this is in elastic programming, the minimal feasible set. This is a very well known problem in mixed in linear programming. This is a very well known problem in linear programming. Okay, because for us, based on our assumption, it does not really matter. Our concern is for all excited locations, we want them to be greater than the excitation threshold. For all locations that are that should not be excited, we want them to be lower than the inexcitation threshold. For us, once this constraint is satisfied, it does not matter to us how much it is satisfied. But if all locations greater than the excitation threshold are equally considered excited. All those lower than the inexcitation threshold are equally considered unexcited. That's why we adopt a mixed integer approach. We define the constraint as breakable constraints, okay, and we want just to count them. How many of the constraints we want? Just our objective is based on their count. Okay, how many of the constraints have been satisfied? Okay, the more the constraints are satisfied, the more I have achieved my objective. Okay, we here, when we define our constraints, we include into them a binary variable. Okay, this binary variable, of course, it's preferable for us that it is 0. If it is 0, then we know that the constraint has been satisfied. If it is not 0, then we know that the formulation had no other option but breaking the constraint. Okay, so the number, actually the summation of the binary variables actually conveys to us the number of broken constraints. Of course, we can weight the number of broken constraints can be weighted by the visual error associated by the broken constraint. Okay, they can be weighted as in this equation by the number of desired to be excited and desired to remain unexcited locations. Okay, and this point will be elaborated on more. When attacking this problem, we were just at the start of the thesis work, and I was not really familiar with the tools that can be used to extract a certain portion of the cortex. And so we just decided to focus on a general problem. We have a set of electrodes on the surface of the cortex, and we want to excite a certain chosen region of the cortex. Okay, we define certain cortical locations that we want to control. We want to have precise control on them. When we decide to excite a certain location, we should be able to excite it selectively. Okay, when we decide to excite a certain group of locations, only them should be excited. So this is a general setup we use. We used also, of course, for safety purposes, there should be a counter electrode. Okay, the counter electrode, the current through it is the negative summation of the currents through all other electrodes. This ensures that we have zero injected, that the injected current is zero sum. Okay, for safety purposes, we tried different locations for the counter electrode in our study, and we tried to use the mixed integer approach and the conventional and nonlinear approach, and the quadratic approach. We use them all, and to see which of the methods is capable of selectively exciting or giving precise control on the locations that we are studying. Okay, this is this is the focality study. Which of the different methods can really excite each of the intended locations selectively? Okay, We defined this measure of focality here based on the number of locations that are excited by mistake. Of course, if the number of locations excited by mistake are 0, the focality is 1. As the number increases, the focality decreases. Okay, in our study we have 400 defined locations that we want to control precisely. We plot here the histogram to compare the different methods. We plot the histogram. By histogram I mean that I have different ranges of focality. We find the number of locations. The histogram bins are the focality ranges, and we find for each method the number of locations that are within each bin. Of course, we find here for the defined method, for the proposed method, for the proposed mixed integer linear approach, we find that most locations are in the bins close to achieving close to 1 focality, while with other methods the focality is much lower. Okay, for the quadratic case we also tried, because of, as we said, it is a disadvantage in the quadratic case is that it assumes that slightly higher than the threshold is equally bad as slightly lower than the threshold. To overcome this, one of the reviewers suggested that we can use an elevated threshold for the location that should be excited, and a much decreased threshold for those that should remain unexcited. So we try to use different margins. These are the different quad cases, and still we found that most of of course the margins did have an effect, but still we found that the achieved focalities at most locations is much lower than that achieved with the desired with the proposed mixed integer linear programming approach. Next, we considered the complex pattern fitting problems. In the complex pattern fitting problem, we defined we defined random examples. In these random examples, we randomly choose in each example a number of locations that are desired to be excited. Okay, and we solve we try to find the optimal currents that can selectively excite the required locations. We use here are the results using the probabilistic approach. Of course, here once again we define the probability of failure based on this sigmoid. The closer we are to these are the two thresholds, the on threshold and off threshold. Okay, if we are at the off threshold corresponds to 100% certainty that location is unexcited, and the on 100% certainty is excited. Between them we have a probabilistic, we can weight it based on the value of the delivered current relative to the most threshold. We can estimate a probability of failure, of course, that based on considering our objective, whether our objective is to excite a location or to leave it unexcited. And we computed the average probability of failure based on this, and once again we compute the histograms, okay, over the examples. Here we find the number of examples, the histogram bins are average probability of failure ranges, okay, and we find the number of examples falling within each bin. We find for the approach, the proposed mixed integer approach, that most of the examples are in the bins corresponding to very low average probability of failure, while for other methods most of the examples have results in the bins corresponding to higher average probability of failure. This is in this study here we try to report the number of missed desired locations and the number of locations excited by mistakes and the inconsistency we defined earlier, the time to solution, and the average probability of failure. We study them for the different methods, and we study them against the number of target locations. How many locations are desired to be excited? Of course, we compute the average of different examples. Okay, So here we find, of course, it is as expected. As the number of locations increase, the problem is more complex. As the number of locations we desire to excite increase, the problem is more complex. We want to related to the inconsistency. Of course, the mixed integer approach is performing the best. Okay, and the same related to average probability of failure. However, related to the number of undesired locations that are excited, we find other methods appear to be giving better results, but actually this is on the expense of they fail to excite many of the desired locations. So this is actually an artificial thing. Also, if we want to force our method to favor to favor not exciting locations by mistake, we can control the weights in the objective function for this purpose. The problem is there is a problem with the timing. The mixed integer linear approach takes much more time. However, we will discuss several this problem really can be, the problem with the timing can be coped with. First, there are applications for which the electrode currents that are required to satisfy the stimulation purposes can be computed offline. We don't need to recompute them every time the problem is can be solved, and the computations can be done offline, and then the computed currents can be applied to the patient. This applies to cases like treating epilepsy, treating migraine. Okay, this is one thing. The other thing is that we can use a case-based reasoning. Based on case-based reasoning, you can solve many problems and store the solutions to these problems in a codebook. When we get a new pattern that is a new desired pattern, we compare it to the patterns that is stored in our codebook. We find the closest pattern to it, and we just retrieve the currents corresponding to this closest pattern. Okay, by this we solve the timing problem. When we discuss the different problems, we spoke of two types of control variables. The first is control currents, and we discussed how to optimally obtain using mixed integer approach. Okay. Next, we discuss the second type of control variables that we said that can be manipulated to achieve our objectives. These are the electrode locations. Okay, how to optimally estimate the electrode location. This is the second problem we tackled, and as we explained earlier, electrode locations can be used to improve the focality of a certain stimulation setup. Okay, however, it cannot be used with complex pattern fitting, because we cannot change electrode locations corresponding to each image. Okay, the problem with optimal estimation of electrode locations is that electrode locations, in contrary to the current, do not directly appear in the mathematical formulation. So we need a mathematical trick to include them within the mathematical formulation. Okay, we will take advantage of the discrete nature of the problem. We actually have, because we defined the problem over a mesh, we have a discrete number of locations, a discrete number of possible candidate electrode locations. Okay, we modify the safety constraint of the electrode currents so that it is defined using a binary variable. Okay, so that if this binary variable is 0, this means the electrode currents is 0, which is effectively amounts to removing this electrode. Okay, by this modification of the safety constraint, we include the electrode variables, the electrode locations, as optimization variables. Okay, next, now since we want to maximize the focality of a setup, we have to solve all the focality maximization problems. There is a focality maximization problem corresponding to each location. To select this location in particular to be able to excite this location in particular selectively. Okay, so we have a set of focality maximization problems equal to the number of locations. We need to merge them into one problem so that we find the electrode locations that achieve the best compromise, that selectively excite all these locations so that each of them can be selectively excited. Okay, so we need to merge the problems into one. To merge these problems into one, we need to define the objective function in a different way. Okay, so we will discuss two possible formulations for the objective function. In the first type of formulation for the objective function, we define a certain required level of focality for each location. That is, that each location we define that it should be excited with accuracy defined by a certain maximum visual error that should not be exceeded. Okay, of course this formula computes the error, okay, the visual error. We want this visual error to be less than or equal a certain defined value. Okay, we define the constraint as a breakable constraint. It's a constraint that is relaxable, can be relaxed. Okay, so our objective is that the number of broken constraints is minimal. Okay, is minimal. So our objective is to minimize the number of breakable constraints, which amounts to minimize the number of locations at which the specified focality is not satisfied. Okay, the specified level of focality is not satisfied. This is the first way of defining the objective function that merges all the problems together. Okay. The second way, in this, of course, here when to find the electrode locations. Okay, our objective is as we said, is to minimize the number of breakable constraints, and we add a constraint that we want to obtain this so that we can find the electrode locations. We say that we want to obtain this level of focality at all locations with an electrode numbers not exceeding a certain n electron x. Okay, so that we want the dummy variables defining used in the electrode current. In the electrode, the safety current constraints, we want their sum, which amounts to the number of electrodes, to be less than a certain maximum value. So we want to achieve a certain level of focality at all locations using a set of using a number of electrodes not exceeding a certain predefined number of electrodes. This is the first formulation. Second formulation, alternatively, we define that we seek that to impose a certain degree of focality, and we want to find what is the minimal number of electrodes that can achieve this desired focality. So in this case, we define also the focality constraints, the focality error specification constraints. We define them, but not as breakable constraints, as mandatory constraints, and instead we make our objective is minimizing the number of electrodes, which is minimizing the number of binary variables used in their constraints, in the electrode currents constraints. Okay, this is the second possible objective function. To demonstrate the power of this proposed formulation, in this time the case study we adopt is really related to the visual cortex, and we defined by this stage of our research I was more experienced and was able to extract exactly layer 4 from the primary visual cortex using suitable software packages. We defined our own meshing algorithm that enables us to define a very accurate mesh sub-millimeter in sub-millimeter range based on using minimal computational resources, and our work is now restricted actually to layer 4 of the visual cortex. Our meshing algorithm is based on classification. Free surface software using minimal computational resources extracts the surfaces of white matter and gray matter and outer skull surface and inner skull surface. Based on classification, suitable classification code, we can classify each point of the studied point with where it is within which of these surfaces. If it is inside the mole, then we are then this is white matter. If it is if it is outside the white matter and inside the rest, it is gray matter. Similarly, you can define whether it is the inner skull or outer skull. So based on this simpler classification code, we successfully we successfully developed a very accurate mesh for our calculations. We next demonstrate what kind of queries our formulations can help, and in what way it can help the designer gain insight. The first problem we study is the problem with why is really finding the optimal electrode locations a complex problem. Why is it a complex problem? We want to answer this question, okay? Actually, because we need to find a compromise. Here we want to excite 4 locations selectively, and we have a total number of 12 electrodes, okay? We want to choose 12 candidate electrode locations. We have 12 candidate electrode locations. We want to find the subset of them that can achieve that can best selectively excite each of these 4 locations, okay? Which subset of them we want to choose out of them 6 electrodes. Out of these electrodes we want to choose only 6, so that these 6 are those who can best excite each location, okay? First we find the 6 achieving using our formulation, achieving the best compromise for all locations. These are shown in blue. Then we find for each location, shown with its same color, which 6 electrode locations are optimal for the green location, which are optimal for the magenta location, which for the yellow, which for the red. So we find each location from its perspective want different electrodes. That is why the problem is difficult. We want to achieve a compromise. That is why to find this compromise we need to solve all problems together, and solving all problems together results in a relatively large, computationally large problem, okay? This is the first query that can be answered using our formulation. The next query, the next type of problem that we will study using this formulation is the max-Fock formulation. By max-Fock, this is the first type of formulation we discussed. We want to find the minimal number of electrodes, the minimal number of electrodes that can achieve a certain that can maximize no, we want to maximize the focality subject to a certain constraint on the maximum allowable number of electrodes. This is the first formulation, okay? So first, for a certain number of candidate locations, we find what is the best. This is the approach we take. For a set of candidate locations, we find what is the best performance that can be achieved if all candidate locations are used. What is the best focality? What is the maximum focality that can be achieved using all available candidate location? Okay. After that, we want to find which electrode location can be considered redundant, so that we can discard them and without them obtain the same bound, the same degree of focality. We studied this for 3 different problems. Okay. In the first 2 problems, we have 16 brain locations, okay, but different number of candidate electrodes. In the second example, okay, the number of candidate electrodes is greater, and we want to find what is the minimum number of electrodes that can achieve the maximum focality bound that we defined. Okay, we find that the defined focality bound, okay, can be achieved for in the first problem using 38 electrodes out of 48 candidate electrode locations, while in the second example we achieved a better bound which is only 2 locations were considered unfocal. yeah, they failed to satisfy the desired bound. Only two locations were found bifocal using 35 electrode locations out of the total of number of 64 candidate electrode locations. So it appears from this that as the number of candidate electrode locations increase, we have a greater chance of achieving better performance using minimal number of electrodes. This is because our formulation is actually a discrete approximation of the continuous problem. The accurate formulation should be continuous. We should have all possible locations. We should have all possible locations defined as candidate location, which of course is naturally not possible, is impossible. So as we increase the number of available candidate locations, we can achieve a solution that is closer to the true the true optimal solution. In the third example, the number of locations we want to control is larger. We have 56 brain locations, okay, and we want to find out of we have the candidate electrode locations are 112, and we want to find what is the minimal number of these 112 candidate electrode locations that can achieve the desired bound, which is the best performance that can be achieved if all candidate electrode locations are used. Okay, we found that in this problem we found that only 99 electrodes can be used to achieve the bound, which is in this case the best thing that we can achieve is only 8 unfocal locations. Only 8 of the locations are unfocal. They cannot satisfy the bound. Okay, they cannot satisfy the desired bound. There is a detail I would like to clarify regarding the previous results. In the Max Fox formulations, the process of the computations proceed in the following sequence of steps. Okay, the first step, we solve the Max Fox formulation that we defined earlier with the constraint on the number of electrodes that they are equal to the total number of available candidate locations. Okay, so we know that this is using this, we are saying that we can use all candidate electrode location. The performance, the degree of focality obtained, the degree of focality obtained using this formulation is termed is called the bound. This is the bound. So we found how many locations were focal. This is the bound. We know that we cannot achieve anything better than this. Okay. After computing this bound, the next steps proceed as follows. Okay, we decrease the number of electrodes one by one, and for each time we decrement the number of electrodes by one, and we resolve, and we find what is the best degree, what is the degree of focality obtained, how many locations are focal according to the specified error. Usually the error we specify is 2 pixels, for example. Okay, the error does not exceed 2 pixels, and we find how many locations satisfying that the error at them, the visual error for estimating does not exceed 2 pixels. If we found the number of locations satisfying the bound, satisfying the best, satisfying the desired degree of focality are equal to the bound, then we know that this number of electrodes is sufficient. Okay, we then repeat. Each time we repeat by decreasing 1 electrode. We continue until we find that decreasing an electrode gives us worse performance. If it gives us worse performance, then we know that this is the number just before it is the minimal number of electrodes that we can use to achieve the bound, so that other electrode locations can be considered redundant. Okay. The next formulation is the mini-elec formulation. With the mini-elec formulation, we specify a bound that we want to achieve. That we want to, for example, we want to find the minimum number of electrodes. Okay, that can be so that at each location, the visual error is less than a certain defined error. Okay. In the first problem, we study 36 brain locations, and we have 180 candidate electrodes, and we define the best maximum, the best delta max, the best visual error we want it to be at all locations that we want. At all locations, we want the visual error not to exceed 3 pixels. Okay. We find that 101 electrodes are capable of achieving this desire. Okay. In the second problem, we study the same 36 locations, but again we increase the number of candidate locations to 144. Okay, and we find that by increasing the number of candidate locations this time, we can achieve the same desired bound. We can not exceeding 3 pixels at all locations, but with only 67 electrodes. In this location, in this problem, we could not prove the optimality. However, the optimality gap that we settled at was 1. This means that we know that the best solution cannot be better than 66 electrodes. It may be possible to achieve the desired bound using 66 electrodes, but not less. Okay. I would like to point out some remarks regarding our approach for electrode locations estimation. The approach we suggested is capable of answering queries that are difficult to answer conclusively using alternative optimization methods. For example, the max-Fock formulation is able to help us get rid of redundant electrode locations. It tells us conclusively what electrode locations we can dispense with without performance degradation. The second formulation, which is the min-elec formulation, similarly helps us for example, if we want to impose a certain visual error, we want it to be imposed on all locations. We don't want it to be violated by any of the locations. It can tell us conclusively whether our goal is feasible or not. So if it is important to us to achieve this visual error, if it is not possible or not useful without it for our application to be useful, then we know for sure that using the configuration we are using now, our goal is impossible. We don't waste any more time. We search for alternative configurations. Such conclusive answers are not possible using alternative methods. The third contribution in the thesis is the time division multiplexing idea. Use suggestion of using time division multiplexing to improve focality. Okay, time division multiplexing is a very well-known idea in many engineering applications. Okay, in communications, when you want to serve a large number of users, you can serve these users by looking at time as if it is divided into consecutive time slots. You serve each user in the time slot pertaining to this user. Similarly, in operating system, if you want several processes to appear to be running at the same time, you assume that time is divided into slots, and you serve each process in the time slot allotted to it. The idea of time division multiplexing is you handle a complex problem by dividing it into simpler tasks, such that only a single simple task is solved within each or is solved within each time slot. How can we apply these principles to brain stimulation? To apply these principles to brain stimulation, we will look at a complex pattern fitting problem as if our tasks is we want to excite a group of locations at the same time. We will consider the task of exciting each location alone as a simple task, because when the number of, as we did see earlier, as the number of tasks or number of targets decrease, the conflicting aspects of the problem decrease. Okay, So we will consider the problem of exciting a single target in each time slot. So if we want to excite 4 targets, then we will allot to them 4 time slots and try to excite each of them selectively within the allotted time slot. Okay. This, of course, this has 2 advantages. The first, as we said, we are solving a simpler problem. The second is, since we are any problem now is decomposed into a set of problems in which only a single target is excited, then we are actually discussing the focality maximization problem. Okay, so if we solve the focality maximization problem of each location and store the results in a codebook, in a table, saying that each location is selectively excited using which currents, then when we want to achieve that, or to implement a time division multiplexing scheme, the implementation of a time division multiplexing solution amounts to looking into the codebook. Within each time slot, we see which location we want to excite, and we retrieve the currents capable of exciting this location selectively. Okay. Luckily, if precise timing if precise control of timing is achieved, it will appear, just as with all time division multiplexing applications, as if we're exciting all locations at the same time. Now, time division multiplexing is essentially an idea that is difficult to verify except using practical experiments. Okay, it requires practical experiments to be verified because it is related to perception. Will we succeed when we evoke each phosphene in a different time slot? Will we really succeed in conveying to the blind person that all phosphenes are evoked at the same time? This is something that cannot be verified except experimentally, and there are no perception models that can help us with this. So what is the least we can do when we are applying a theoretical framework, so that we are convincing that using time division multiplexing can really contribute to stimulation research? What kind of theoretical framework can be adopted? The kind of theoretical framework that can be adopted, from my point of view, should handle 3 issues clearly. The first issue, it should be clear that we are aware with the complex dynamics of the system, that nothing of the complex dynamics of the system is looked out, because it is the complex dynamics of the system that will say if time division multiplexing achieves its goal as being as serving all tasks at the same time or not. So the complex dynamics of the system should be addressed, should be studied, and based on them we should decide how to choose suitable time slots, how to exactly implement time division multiplexing in a stimulation, in a brain stimulation context. This is the first thing. The second thing is, of course, we need to show that using time division multiplexing really gives an improvement over direct targets excitation, an improvement that is worth pursuing. Does really time division multiplexing make a difference? To prove this, from my point of view, we should do 2 things. Okay, of course, we should solve the same problems using time division multiplexing and using direct optimization by targeting all location, or by exciting all required target locations at the same time, and by using time division multiplexing. Examples should be solved using both methods, and the visual error obtainable using both methods should be compared. Okay, but what is important, even if time division multiplexing does make an improvement, in which kind of examples? Does the kind of examples it makes an improvement is really have practical importance? The complex example in which it makes a difference, the complexity, what the aspects making them complex make a difference, are important. For this, we need to study the complexity factors, the factors that make a problem complex, and show to researchers that these aspects have practical importance. Okay. The third thing What if time division multiplexing fails in really giving the patient the impression that all phosphines that are evoked at the same time? If the patient sees phosphines being evoked sequentially, will this still, but we are evoked sequentially but at accurate locations, contrary to direct optimization. With direct optimization there will be false phosphines giving false impressions of obstacles. Which really is better, to have these false phosphines, or to use time division multiplexing and see obstacles sequentially, actually see their locations sequentially? If we see the locations sequentially, will time division multiplexing still be useful? If we reason about parts of the image in a sequential manner, will time division still be useful? This is the third aspect that we should study. From my point of view, the most important problem regarding our understanding of neuronal dynamics is to guess the following. Okay, in time division, if we plan to use time division multiplexing, it has an advantage that in each problem we have only, in each time slot we will have only one target location that we want to excite. This is actually the focality problem. This means that if we solve the focality problem for all location and store the solutions in a codebook, then we can simply, in each time slot we simply find which location we want to excite in this time slot, and we retrieve from the codebook the corresponding currents that are capable of exciting this location selectively. Okay. However, the problem is that with the duration of time slots is of course expected to be small, and we know that even if a location in a certain time slot, now we have consecutive time slots. Okay, if we have, even if in a certain time slot the location does not receive currents capable of exciting this location in particular, the currents it receives in the history it receives in previous time slots affects its state. It has a different initial state. Okay. Now, when we solve the focality maximization problem and store the solutions in a codebook, we assume that thresholds are fixed because we solved the problems offline and stored the solutions. However, the history of in each example, the history of previous time slots, the input each location received in previous time slots affects its initial state and so affects its thresholds. So we need an approach for choosing the thresholds that we use in building the codebook, so that the codebook can hold for almost all examples with a high degree of probability. So we know in most examples the thresholds based on which the codebook have been decided will work in most examples. Okay, for this we use a probabilistic threshold estimation approach. We study a large number of examples. Okay, and we find for each sequence of slots what are the different initial states they can result in. So we have a range of different initial states that we expect based on history, on different random histories that we try and we simulate. Okay, we choose the thresholds such that for all those studied histories we have a high probability that this location will be excited, and this is the excitation threshold. Similarly, for a range of expected histories, the history is exemplified in the initial state it will result in the coming slot. Okay, so for all the range of expected histories, what is the threshold that is safe to guarantee that the location will remain unexcited with a certain probability, with a certain specified degree of reliability. Okay, so we will use this probabilistic approach in estimating thresholds. Second thing, to simplify the problem slightly so that the expected thresholds for the time division case are not much higher for the on thresholds and lower for the off threshold than those expected when we use direct optimization targeting all locations at the same time. We want to make the differences between the direct case and the time division multiplexing case not so large. we try to insert gaps. We insert gaps between slots. So our scheme is as follows. If we have 4 locations we want to excite, so in the first time slot we give the currents for the first location, and then we stop for a gap. No inputs are presented to the stimulation setup within this gap. Then in the second time slot we give in the inputs, the input electrode currents that should excite the second location, and then we wait for a silent gap. And similarly then we feed the inputs to excite the third and fourth location. All have gaps in between. Okay, these inserted gaps, they make the firing rate of neurons low. Okay, but at the same time they guarantee that the neuron or the brain location have time to return to a state close to the rest state, so that we don't need to elevate the thresholds considerably. Okay, so this is regarding the offline stage, and that depends on our understanding of neuronal dynamics. So now regarding, as we discussed in the previous slide, the offline stage of time division multiplexing involves determining a suitable probabilistic threshold, and then solving the focality maximization problem using this threshold and storing the results. Okay. What about the online stage? During the online stage we are presented with an image. Okay. Of course, the image contains a set of obstacles. Okay, corresponding to them, we want to evoke a set of phosphines. Corresponding to that, we want to excite a group of target locations. Okay, how do we excite this group of target locations using time division multiplexing? Of course, we know that when the results stored in the codebook, every element will be common between several sets. Actually, because when we excite a location, some locations are excited together with it as a side effect. We don't actually achieve perfect selection. Okay, so when we are encountered with a group of location, it may be better to choose when we look through what sets to choose. If some of them may be already excited together as a side effect. Using this concept, we may be able to minimize the visual error. Actually, we are solving a minimal subset cover problem. We want to choose the minimal subset that covers all the targets we want with minimal visual error. Okay, this can be solved using 2 approaches. Okay. The first approach is an exact approach as an integer linear programming problem. Where we insert 2 types of constraints. Okay, we define membership variables XS. These membership variables, they are 1 if a certain set is chosen, and 0 if it is not chosen. For the desired target locations that we want to excite, the summation for each of them, the summation of membership variables should be greater than 1. Okay, this assures that at least one of the sets containing it has been chosen. At the same time, for all locations that should not be excited, we define a constraint that for them, the summation of the membership variable should be less than or equal the number of sets it is in which they lie. Okay, or 0, preferably 0. It should not be chosen. Okay, the variable, there is a binary variable that we define here, Lj, that is 1. Okay, when it is 1, it indicates that this undesired location has been excited. Okay, when we insert this binary variable into the objective function of the problem, this assures that this constraint, that this Lj is not made 1 except if it is unavoidable to excite this undesired location. Okay, this is the exact value. The greedy algorithm simply proceeds by choosing. First, we look at the first target location we want to excite. Okay, and we see which sets include it, and we choose the set that contain the maximum of achieves the best Euclidean area, contains most other other locations that need to be excited with minimal unexcitations, okay, with minimal undesired excitations. And we then we delete the targets that have been excited in this slot and continue with remaining targets until we are sure that we've chosen the sets that guarantee that all targets are excited. So it proceeds sequentially, okay? Now we come to the first aspect of our theoretical framework of studying time division multiplexing. As we said, we want to study the factors that contribute to problem complexity. Okay, these factors can be mainly divided into factors under my control and factors defined by the problem. Okay, it is more important for us that time division multiplexing makes difference with the factors that are uncontrollable, that are defined by the problem. We studied different factors that, like the number of electrodes, the effect of the number of electrodes on the problem complexity, the effect of the distance between the electrode centroid and the target location centroid, the distance between the counter electrode and the target location centroids, number of targets that need to be excited, the total number the total number of members of the total number of location within the volume bounding within the volume we have the target location are bounded within a certain volume. How many of the cortex locations that we are studying are within this volume? Okay, this is a measure that tends to convey to us whether the volume we are studying, whether the volume our example is concerned with is crowded or not. Of course, as it is more crowded, the more the problem is complex. Okay. Also, the maximum interdistance, the maximum distance between the targets that need to be excited and the minimum distance between them. The maximum distance conveys insight about the span of the pattern, the span of obstacles we are how far they are from one another, and the minimum distance is a measure of resolution, the minimum distance between the targets. Also, we study the relative volume, the ratio between the volume bounding the members or the targets that we need to excite to the total volume studied, to the total volume occupied by all brain locations that we want control. Okay. To study the effect of these complexity factors, we define two approaches: a computational approach and a graphical approach. Okay. First, regarding the number of electrodes, and for the number of electrodes, we studied them separately by, of course, we simulate several examples. The examples are random. The choice of the targets are random, and the choice of the number are random. Okay, and we record the visual we record the parameters that we use, like the number of electrodes and the value of the complexity factors that we study in each example, and we record the visual error from the results. So we record the parameter and the visual error of each example. Okay, for the number of electrodes, of course, it is expected, it is intuitive that as the number of electrodes decreases, the problem is more complex. Also, we tried different maximum electrode currents. Of course, also when we impose greater restriction on the allowable maximum electrode current, the control is more difficult. We can see this by seeing that the total visual error, we see that the total visual error in this histogram, this histogram, we see how many examples fall within the bin of each of different ranges of visual error. Okay, so we expect that as we increase the number of electrodes, the visual errors actually improve. When we see that the visual error improve as we increase the number of electrodes. However, we noticed that, of course, and as we decrease the current, as we increase the allowable maximum current, also the visual error improves. We achieve lower visual errors in most examples. So with greater electrode number and higher allowable maximum current, we achieve better results. Okay. However, we also notice something, that from the computational point of view, as the number of electrodes exceeds a certain bound, we see that the problem becomes computationally complex. The size of the problem becomes large, and it becomes difficult to reach the optimal solution within the allotted time. That's why we can see that for very large electrode numbers, we see that the performance ceases to improve, because just we are not able to reach the optimal solution within the allotted time. Okay, this is regarding the study of the electrode number. Okay, regarding other complexity factors, we study them using two approaches: a computational approach and a graphical approach. In the computational approach, we consider there are three indications of a problem complexity. If we are not able, if the problem turns out to be infeasible, this indicates complexity. If we are not able to reach an optimal solution within the allotted time, this is an indication of complexity. If we did reach optimality, but we found that the error we achieved is a high visual error, this is an indication of complexity. So there are three aspects that indicate complexity. Okay, we define two computational measures. The first computational measure, computational performance measure, we study the range of each complexity factor within the infeasible examples, okay, over its range over all examples. Okay, if we can see that there is a particular range of the variable achieving feasibility, then we know that they are leading to infeasibility. Then we know that this factor makes the problem complex and makes it more liable to be infeasible. This can be computed similarly for non-optimality or failing to achieve optimality. So if we can define that a certain range of the variable leads to infeasibility or leads to non-optimality, then we can say that there is a correlation, or there is a strong correlation between this variable and between problem complexity. Okay, so we can decide that this factor is complex. Okay, the result, the result, okay, the results are shown in this table for both the ordered pair for two different electrode current limits. Okay, the second computational measure that we define is the probability related to the visual error. We study for each factor what is the probability of increasing or decreasing this factor increases the visual error. This is computed by comparing each pair of examples pairwise, and we see when study for each pair whether increasing this factor increases the visual error or not, and based on this we can compute probabilities. Okay, the probabilities also are shown in this table. For the graphical approach, with the graphical approach we plot the value of each variable, of each complexity factor. Sorry, the value of each of the complexity factor against the visual error. As we can see, it appears that they are correlated. Indeed, the increasing value is increasing the certain complexity factors does indeed increase the visual error. We study both the direct and inverse relations. We study increasing and the decreasing aspects, and we see that they appear to be correlated indeed, that complexity factors indeed increase the visual error. Okay, we can summarize the results from the previous figures and tables in the following. We can say that the minimum distance between target location is the factor that influences the most failure to reach optimality and failure to achieve feasibility. The problem becomes infeasible. So this is the most factor, and this is logical, because as the distance between targets, as the minimum distance between all targets becomes small, we have a pattern. We need a pattern with high resolution. actually, because we need to discriminate targets that are very close to one another, and still there are neighbors in between them that should not be excited. Okay. Also, we find that it is difficult to achieve low visual error as the number of targets increase, of course, because the conflicting aspects become more evident, and also as the number of targets within the volume increase, because as the number of locations within the volume of the targets increase, because as the number of locations within the volume of the target increase, this means that we have more locations that we don't want to excite while exciting the intended target locations. Okay. We find also that the maximum distance and the relative volumes also increasing them makes the problem more difficult, because as the pattern spans a larger area, we want to span a larger volume. When we want to span a larger volume, this means that we have also more conflicting aspects appear. There are more locations that we need to avoid exciting while exciting the targets. So we can say that again, aspects relating resolution, the finer the resolution we want to achieve and the larger the span we want to achieve, the more complex the problem is. Also, as the number of as we said earlier, as the number of electrodes and the maximum allowable current number both decrease, it is more difficult to have to control the visual error, to achieve low visual errors. The problem becomes more complex. Now we come to comparing the results between solving the same examples using direct optimization, exciting all targets at the same time, computing the current at the same time, and by using time division multiplexing. Okay. We will see that time division multiplexing we will compare 4 different aspects. Okay. The first aspect is the capability of obtaining a feasible solution within the allowable time, the capability of obtaining a provably optimal solution within the allowable time, the achievable total visual error using both methods, and the time to reach a solution. These are 4 aspects that will be used in the comparison. Okay. Now here we see that first here we see that when we compare, I want to show these figures in details. Here we see, of course, we come back to the point we said earlier. As we said earlier, that achieving feasibility and achieving optimality is more difficult, okay, as the number of electrodes decrease, right? Okay, as we use fewer electrodes, when we use fewer electrodes, it becomes difficult to achieve feasibility, to achieve optimality. As we said, for optimality, the curve again, it becomes again difficult to achieve a good visual error as the number of electrodes to reach the optimal solution, as the number of electrodes increase due to computational aspects of due to complexity of computations. Okay. However, this applies to direct optimization only. These aspects do not apply regarding the difficulty of achieving feasibility or arriving to provable optimality. These are all only related to using direct optimization. However, when we use time division multiplexing, we are solving a simple problem. Our target is just to excite a certain location selectively. Okay, so since our target is simpler, then if the location is reachable, then we know that we can excite it selectively. So there is no issue regarding feasibility. Also, if the solutions stored in the codebook are optimal from the focality maximization problem solution. And if we use the minimal subset cover approach, then we know that the solution we obtain is an optimal solution. Okay. Also here we compare. We see here the degree of we plot the degree of improvement. Okay. We plot the degree of improvement obtained using time division multiplexing over using direct optimization. We simply we subtract both errors, the error using direct optimization from that using time division multiplexing, and we plot this improvement versus the visual error. We see that it is in particular for the examples that direct optimization fails to achieve a good visual error. In these examples in particular, the degree of improvement is evident. We see that it increases as the visual error of direct optimization increase. The degree of improvement achievable using time division multiplexing also increases. As for the time, of course, because using time division multiplexing is a codebook strategy, we just retrieve solutions. Of course, time division multiplexing from a time to solution point of view is much better, is far much better than using direct optimization. We now come to here the results are shown in this table. Okay, we see in this table we compute the probability. What is the probability that time division multiplexing is superior? Okay, we complete them for the cases of two thresholds achieving reliability 0.93 and 0.97. Okay, and we find that for whether we use the minimal subset cover approach or whether we use the greedy approach, for both cases we find that time division multiplexing performs better. The probability of it performing better exceeds 90% for all study examples. Here we see the graphical results. We study in one example where we want to, this is a visualization of the results. In one example here we see these are the desired obstacle locations. These are the locations that the patient will see if we use the direct optimization. Here this is the third one, okay, in green, and these are using minimal subset cover time division multiplexing. Of course we see it is clear that using minimal subset cover time division multiplexing shows the obstacle location much more accurately, while direct optimization almost fails to show the obstacles in the correct location. There is no discrimination. There is almost no discrimination. It almost shows obstacles everywhere. Okay, so the pattern offered by direct optimization is not that useful, but that offered using time division multiplexing is much better and much more accurate. And the same applies to the case when we use greedy time division multiplexing. Using the greedy approach is faster. It is faster. Just looking for each location in which set it exists and choosing the set leading to the minimal Euclidean error and deleting it and proceeding to the next and so on. This is a very fast approach. Of course, using integer programming is much slower, but still both of them obtains comparable results. Now the psychological experiment. We have no means to test the aspects regarding imperfection of implementation. What if the patient reasons about different parts of the image sequentially. So instead we developed a simple psychological experiment. In this psychological experiment, it consists of two parts. In the first part we have handwritten Arabic sentences. Okay, we will divide these sentences into blocks. Okay, and we will show them to the volunteers block by block. Okay, the blocks are, we scan the blocks. Each time only a single block is shown against a black background. Okay, and we repeat the sequence. We continuously repeat the sequence. We tried different frame rates, 75 frames per second, and a much lower frame rate, 1 frame per second, I think. Okay, the second part of the problem, we have an image with puppets. We divide the image into cells. Okay, and similarly in each we will show the volunteers videos. In each video only a single cell will be shown against a black background. Okay, and we iterate between the different cells. The task will be, of course, for the handwritten for the handwriting, the task is recognizing what is the sentence written. For this task, the task will be, we want them to, a certain puppet, we want them to localize the puppet within the image, in which cell this puppet exists. Okay, we showed the videos, and 14 volunteers tried the experiments with us. We tried two different block sizes. We tried small block sizes, 16, using two different block sizes. Okay, for the 16 and 4, these are related to the handwritten. For here, for the puppet image, we had 24. Okay, and I think also they were 4. Okay, so we tried two different block sizes, small block sizes and large block sizes. Okay, and we tried two different frame rates, 75 and 1 frame rate. The results from the experiment, without any training, the subjects were able to extract useful information. They were able to locate Safa. They were able to read the sentences. We can see that for the 16 tiles, 75 frames per second, with the for the puppets, the larger the frame rate, here we can see the best performance is achievable for the puppets case. Okay, is using a large tile size, because it is clear what puppets are in each tile or large cells, and using whether using a large frame rate or small frame rate, it really didn't make much difference. Of course, the slower frame rate was better. For puppet recognition was better. It gives them time to reason about the different cells. Okay, for the sentences case, the best performance is achievable using using large tiles, small number of tiles that are, each of them are large, and using a high frame rate. The high frame rate for the sentence case was better, 100% recognition. They all read the sentence successfully. What we can say from this, that we can say that time division multiplexing can convey useful information if the subjects, regardless of the imperfection of the experiments, they were able to extract useful information. It is expected that with training, the subjects can extract useful, the patients can extract useful information. Aspects like the frame rates, what exactly to show within each time slot can be negotiated based on experiments. Based on experiments, we can see what is better for patients. Now we would like to summarize. I would like to summarize the thesis contribution and learned lessons. The main thesis contribution is that it adapted a complex real-life problem, which is the problem of visual prosthesis design, for the practical implementation to really be optimal, we need to investigate an alternative to those used in the thesis. In the thesis, to estimate the parameters like the threshold and the transfer matrix, we use computational models, finite element method, and the Hodgkin hypothesis model. Of course, there are many unmodeled factors. If we want really to do optimization in real life and get a solution that is truly optimal from a practical point of view, it is better to estimate these parameters, the threshold and transfer matrix, based on practical measurement. The same procedure used computationally to estimate the transfer matrix can be used, but instead of using finite element solution, we can use the results from scanning to show to the blind
person a pattern of obstacles shown by phosphines, a pattern of obstacles shown by phosphines. And I expect that by training, the patient will be able to navigate in complex environment based on these phosphine patterns conveying the location of obstacles in the environment. What if we do use augmented reality to try this with healthy persons? We use special goggles so that they see the phosphines corresponding to obstacle location, and they try to navigate and they investigate their behavior, and they try to navigate based on a group of light spots conveying the locations of obstacles shown in a part of their visual field and not all the visual field, by investigating the reaction of healthy subjects and how they navigate based on these patterns. I can derive design rules for myself. I can come up with suggestions on how to improve my designs, on how to define the different parameters of the pattern used to represent the obstacles, how to tune the different parameters available to me, so that the training procedure of the patients is expected to be more fruitful and easier. Okay, of course, using robust optimization is important. By insert, of course, there are uncertainties in the parameters used in the optimization. Uncertainties in the transfer matrix values, uncertainties in the thresholds. So by using robust optimization, I can be more sure that even under the uncertainties, the computed currents will remain optimal. Okay. Also, one practical experiment to try, we can try to evoke higher visual entities, higher than phosphines. Also, another direction
for future work is relaxing the quasi-static
assumption. Relaxing the quasi-static assumption is important because there are similar applications to brain stimulation, okay, in which our approach mainly could give us high control or a high degree of control on the electromagnetic field within the brain. Okay, in general, having control on the locations we want to influence without affecting other locations, this can have other important applications, like with hyperthermia, for example. In hyperthermia too, we want to control the field so that it only affects the cell